Okay, so this is lesson 11, chi-square tests. So first we're going to start with talking about a goodness of fit test. So this can be conducted when there is one categorical variable with more than two levels. So first you're going to calculate the expected counts. And just to make sure that you can use a chi-square test, if the expected counts are 5 or greater, then you can use a chi-square test. But if any expected count is less than 5, then you would use a randomization test. So a goodness of fit test compares observed counts to expected counts. So observed counts is the number of cases in the sample in each group, and then you have to compute your expected counts given that the null hypothesis is true. So in this case, the number of cases you'd expect to see in each cell if the null hypothesis were true. So you calculate expected counts and then compare them to the observed counts that you observe when collecting your data. So you calculate expected counts in the formula below by multiplying your total sample size times the proportion of whatever group you're calculating for. And then to calculate your chi-square test statistic, you subtract the observed minus the expected, square that, divide it, and then you add up the total based on the total number of counts. So a chi-square distribution is similar to a t-distribution in that it varies based on your degrees of freedom. So the way you calculate degrees of freedom here is the number of groups minus 1, which is similar to that of the t-distribution, except it's the number of groups instead of the sample size. So to find the p-value for a chi-square distribution, we have to use the area under the chi-square distribution to the right of the test statistic. So when we're calculating that p-value, it'll always be a right-tailed test. So we're going to have a similar 5-step hypothesis testing procedure as you've seen before from your material that was on your midterm. So the similar steps. So your step 1 would be to check your assumptions and write your hypotheses. So here you can write your hypotheses first, which your null hypothesis will contain your all of your equalities, and then the alternative will have at least one population proportion that's not specified in the null, so one of those will not be equal to another. And then your assumptions are that all expected counts must be at least 5, which I already mentioned before, and you again calculate your expected counts by multiplying the total sample size by the proportion. And then once you check your assumptions, write your hypotheses, you can compute your test statistic, which we know is similar to the other procedures before. And you calculate your test statistic by comparing the observed and expected counts from all of your groups here. And then you would just add them all together, and that would be your test statistic for your chi-square. So it's that formula below to calculate the test statistic. Once you calculate the test statistic, it's pretty much the same as we've been going before. So you're going to determine the p-value using a chi-square distribution. Your degrees of freedom here, again, is equal to the number of groups. Make sure you use the number of groups, not the sample size. So the number of groups minus 1, and then the p-value is under that distribution to the right of the test statistic. So you're taking a right-tailed test. And then after that, once you get your p-value, you decide whether to reject or fail to reject the null hypothesis. So if your if is less than or equal to alpha, you're going to reject the null hypothesis. And if your p-value is greater than or equal, if your p-value is greater than alpha, then you will fail to reject the null hypothesis, not equal to, that should be if the p-value is greater than alpha, not equal to, Okay. And then after you decide whether or not to reject or fail to reject the null hypothesis, you're going to state a real-world conclusion, which is just addressing the original research question based on whether you rejected or failed to reject the null hypothesis. Okay, so next is the chi-square test of independence. So this is used to test a relationship between two categorical variables. So you will compute expected values for cells in a two-way contingency table. And currently, when you're computing the expected values, you assume that the two variables are independent so that they are not related to one another. They're independent of one another. And you use a similar 5-step hypothesis procedure to calculate this test of independence to see the relationship between two categorical variables. So again, we're going through that same similar 5-step hypothesis testing procedure as before. There's some differences here, so just note those. So again, you're going to check your assumptions and write your hypotheses. Here, our assumptions are again that all expected counts must be at least 5, but then you want to make sure that the sample is randomly drawn from the population as well. Here, when we write our null and alternative hypotheses, our null hypothesis will show that there is not a relationship between the two variables, and the alternative hypothesis shows that there is a relationship between the two variables. So the difference between the null and alternative hypothesis here is just that the null hypothesis represents independent variables, and then the alternative hypothesis represents two dependent variables. So once you have your hypotheses, you're going to compute your test statistic again. Before computing your test statistic, you want to compute the expected cell values in the formula on the right there, and then you'll compute your chi-square test statistic, which is similar to the one before. So step 3, you're going to determine your p-value again. Here, with the independent testing, you're going to have a different degrees of freedom, so you're going to be using the same chi-square distribution, but here there will be a different degrees of freedom. Your degrees of freedom will use the table that you're provided, so you will calculate the number of rows in your table and then subtract 1, and then multiply that by the number of columns to -1 as well, and then that will be your degrees of freedom. And then again, your p-value is just under the distribution to the right of the test statistic, so it's a right-tailed test. Then you're going to make a decision whether to reject or fail to reject the null hypothesis. Again, there's that typo. So it's just greater than alpha. It's not greater than or equal to alpha. So if your p-value is less than or equal to alpha, you will reject the null hypothesis. If it is greater than alpha, you will fail to reject the null hypothesis. And step 5, again, to state a real-world conclusion addressing the research question based on your previous decision. Okay, so next we're going to talk about relative risk. So if you remember before, earlier in the semester, we talked about risk, which is used to describe the probability of an event occurring. So you calculate risk by the number with a certain outcome over the total number. So here, for example, if you said 45 out of 100 children get the flu each year, the risk is 45%. So next we're going to introduce relative risk, which compares the risk of an outcome in two different groups. So instead of comparing one outcome to the total, we're going to compare one outcome to the other group. So it would be the risk in group 1 divided by the risk in group 2. So here, you want to make sure that you calculate risk for each groups, and then you compare it. Relative risk is just comparing the risk between two groups. So for an example, suppose that the risk of a child getting the flu this year is 0.45, and the risk of an adult getting the flu is 0.10. What is the relative risk of children compared to adults? So to calculate the relative risk, you just compare the risk in group 1 to the risk in group 2. So here the risk in group 1, since we're comparing children to adults, children would be group 1, so it would be 0.45 as the risk of a child getting the flu, compared to 0.10, which is the risk of an adult getting the flu. And then once we divide those out, we get 4.5. So the way we would say our answer is that children are 4.5 times more likely than adults to get the flu this year. Okay, so that was a pretty quick summary of what you guys did this week, so we're just going to go through a few review questions. So when reviewing when randomly selecting a card from a deck with a replacement, are we equally likely to select a heart, diamond, spade, and club? I randomly selected a card from a standard deck 40 times with replacement. Calculate the expected count. So pause, take a few seconds to go over that. Okay, we're gonna go over the answer. If you're not ready yet, you can just pause. But the answer is A. So we calculated 10 as the expected count. So the proportion of this is 1/4. So so we get 1/4 because you see in the problem that all of the cards are equally likely to be selected, either a diamond, heart, diamond, spade, and club. So there are 4 possible options that all have an equal chance of being selected. So 0.25 is the proportion that one would get selected. So once we have our proportion, which is 0.25, our sample size is 40, and we just multiply those together and we get 10. Okay, so calculate the degrees of freedom for the chi-square test of independence using the data on the right. So take a moment, pause, and we'll go over in a few seconds. Okay, if you didn't get your answer yet, pause, but I'm gonna go over the answer now. So the answer is C. So for the chi-square test of independence, we don't use the number of groups minus 1, which is what we use for the normal chi-square degrees of freedom. Here we use the number of rows minus 1 times the number of columns minus 1. So the number of rows here is 2. We have the men and the women, and then we subtract 1 from that, we get 1, and then compare it to the number of columns, which is 2, yes and no, and we subtract 1, we get 1. Once we multiply 1 and 1 together, the answer is 1. Okay, so our last review. Suppose 7% of teenage girls have asthma compared to 5% of teenage boys with asthma. Using the females as group 1, what is the relative risk for girls compared to boys? So take a few seconds, we're going to go over. Okay, the answer here is A. So we're comparing females as group 1 compared to boys, so that means the females will be on the numerator in the equation, and the males will be the denominator for the equation. So we're given the risk for girls and boys, so we just fill in the blanks there. So 7% risk for group 1 over 5% risk for group 2, and we get 1.4. So we can conclude by saying that the risk of asthma is 1.4 times as great for teenage girls as it is for teenage boys. All right.